to the next point. We should ensure whatever we see is clear.
That means work is being done. We can see that it is in opposite direction. Hello, learners at home. Welcome once again to another physics lesson on radio and television e-learning program of Ministry of Education, Kaduna State. My name is Hassan Buki. Today we shall be considering the topic, elastic properties of solids, part 1. In our outline, we have definition of terms, then Hooke's law, experimental verification of Hooke's law, and then finally at the end, you have an assignment to do at home. Introduction. Now, in the study of particle nature of matter, we learned that molecules of solids are very closely packed together, and they are held in a relatively fixed position by strong intermolecular forces. And as a result of this, the molecules of solids cannot be easily displaced by an external force, unlike in the case of liquids and gases. However, if the external force is strong enough to cause a deformation or change or distortion in the shape of the solids, as soon as the external force is removed, the solid regains its original shape and size. And this property of the solids to regain its original shape and size when the deformation force is removed is known as elasticity. And the materials that exhibit this ability, they are known as elastic materials. And examples, we have rubber band, spring, ruler, etc. Now, a ruler, you can apply force to bend a ruler. When you remove the force, it will go back to its original shape and size. We go to definition of terms. One, elasticity. And we say elasticity is the property or ability of a material to regain its original shape and size after the deformation force has been removed. Next is elastic material. An elastic material is one that regains its original shape and size after the deformation force has been removed. Now we go to Hooke's law. Hooke's law states that the extension in bracket small e of an elastic material is directly proportional to the applied force in bracket capital F, provided that elastic limit of the material is not exceeded. That is the condition under which Hooke's law is obeyed, that the elastic limit of the material is not exceeded. So mathematically, we have capital F to be directly proportional to small e. Now we have capital F to be equals to capital K small e. And we call this equation 1, where our capital F is our applied force in Newton. Small e is our extension in meter. And K is our constant of proportionality, and it is known as the elastic constant or force constant or stiffness of an elastic material. Now from equation 1, if we make K the subject of the formula, we will have capital K to be equals to capital F over small e, and we call it equation 2. The unit of K is Newton per meter. From equation 2, we can see that we have ratio of force to extension. Force is in Newton, extension in meter. Automatically, that gives the unit of our constant K as Newton per meter. Elastic constant or stiffness of an elastic material is the force required to give a unit extension. Now, next we will look at the experimental verification of Hooke's law. We have the experimental setup as can be seen in the diagram. We have retort stand and clamp. We have our spring. We have a scale pan. Then we have our weight. We have our meter rule. Now we say the experiment is set up as shown above. Now the first thing you do is to note the initial pointer reading and record it as L0. That is when it is not carrying any load. Next thing is to place a load on the scale pan and then note the new pointer reading and record it as LF, which means final length, while our L0 is our initial length. Now the extension E will be equals to the final length minus the initial length, which is L subscript small f minus L subscript 0. Now you repeat the experiment with 4 or 5 different loads and then find their corresponding extensions. Then you keep your readings in a tabular form, and then you will be required to plot a graph of load against extension. So here we have the diagram, the graph showing load against extension. We have our load along the vertical axis and then our extension along the horizontal axis. Now, if we plot this graph of load against extension, it will be seen that it will be a straight line graph passing through the origin. Now, we have our triangle here, which signifies the slope of our graph. Along the vertical, we have change in load. Along the horizontal, we have our change in extension. The graph of load against extension when plotted gives a straight line graph passing through the origin. The slope of the graph when calculated gives the value of the elastic constant or force constant or spring stiffness or spring constant. That is our K. So any of these names, they mean the same thing, either elastic constant, force constant, spring stiffness, or spring constant. Now, going back to that graph, our slope is change in load over change in extension. Load in Newton, which is our force, our extension in meter, which is length. And we've seen from equation 2 that force over extension gives us our elastic constant. So therefore, we have slope to be equals to change in vertical over change in horizontal. And therefore, slope will be equals to change in load over change in extension. Therefore, our slope S will be equals to constant K. Now, alternatively, it could be graph of extension against load. And the slope of the graph, when calculated, will give us 1 over K. And from there, we can find the value of our constant K. Now, we have a second graph here. We have load in Newton against extension in meter. And it is a graph of load against extension up to breaking point. Now, first we have a straight line graph up to point A. Then from A to B, we can see there's a change. There's a curve. Then from B to C, a curve also. Then from C to D, another curve. Then from D to E, we can see that there's a curve, but it is a broken lines. So from the graph, we say point A is our proportional limit. Point B is the elastic limit. And point C is yield point. Then point D is the point where we have maximum load. And then point E is the point of breaking, and we call it breaking point. Now, the proportional limit is the point up to which equal increases in load produce equal extension of the material. So we say up to this proportional limit, Hooke's law is obeyed. Elastic limit, which is point B, it is the limit beyond which if a material is stretched, it does not return to its original shape and size when the stretching force is removed. That is the point whereby if the elastic material is stretched, for example, a spring, if it is stretched beyond this elastic limit, when the force is removed, it will never go back to original shape and size again. Then our yield point, it is the point beyond the elastic limit where the material begins to undergo plastic deformation. So now we look at examples. Example 1, it says, the table below shows the extension of a spring when increasing loads are hung on it. We have our table. We have on the first row, we have load in Newton. The second row is extension in centimeter. And we have first load 0, corresponding extension 0. We have the next one 3 and 1. We have load 6, corresponding extension 2, 9 and 3, 12 against 4, 15 against 5, 18 against 7, 21 against 12, 24 against 20. Now the question says, according to the table, up to what load does Hooke's law apply? And then what load should produce an extension of 2.5 centimeter? Now solution. Let's go back to the table again. If we look on the table, from 0 to 15, the increase in load, now the increase in load all through up to 24 is constant. It increases by 33 Newton. Then the extension increases by 1 centimeter up to when the load is 15 Newton. After 15 Newton, at 18, the increase is more than 1. So we can say, therefore, up to 15 Newton, Hooke's law is obeyed. Solution. Hooke's law applies up to 15 Newton because from 0 to 15, we see that the extension increases by equal amount. Now the second part, from the table, I'm taking my load F to be equals to 6 Newton. Its corresponding extension is 2 centimeter. And if we convert 2 centimeter to meter dividing by 100, it will give us 0.02 meter. Elastic constant K is unknown. Therefore, from equation 2, we know that K is equals to capital F over small e. That means force over extension. Now, substituting in our values, we have 6 divided by 0.02, and that gives us K to be equals to 300 Newton per meter. Now, within that limit where Hooke's law is obeyed, whatever value of force you take and its corresponding extension, it will give you the same value of the constant K. Now, when E, our extension, is 2.5 centimeter, that's what the question is asking us to find the load that will correspond to extension of 2.5 centimeter. Converting 2.5 centimeter to meter, we have 0.025 meter. The load or force F is unknown. From Hooke's law, where we have F to be equals to KE, substituting in our value, we have 300 times 0.025, and that will give us 7.5 Newton, which means that 7.5 Newton will produce an extension of 2.5 centimeter. Example 2. A pointer attached to a spring points to the 10 centimeter mark when there is no weight hanging on it. When 0.4 Newton weight hangs on it, it points to 13 centimeter. Where does the pointer point to? If a weight of 1 Newton hangs from the spring, what weight will be required to make the pointer point to 14.5 centimeter? Solution. We have our original length L0 to be 10 centimeter, which gives us 0.1 meter. Final length LF is equal to 13 centimeter. Converting to meter, we will have 0.13 meter. Now, extension E is equal to final length minus initial length, which is 0.13 minus 0.1. That gives us 0.03 meter. Our force F is 0.4 Newton. Spring constant K is unknown. Now, going back to our formula of K is equal to F over E, substituting in our value, we have 0.4 divided by 0.03, and K will be equal to 13.33 Newton per meter. Now, when F is 1 Newton, extension is unknown. Now, if we make extension the subject of the formula, we will have extension E to be equal to F over K. Substituting in our values, we will have 1 divided by 13.33, and that gives us 0.075 meter. Now, the pointer reading will be equals to 0.1, the initial reading, plus this new extension 0.075. If we add them, that will give us 0.175 meter, or in centimeter, it will be 17.5 centimeter. That's if we multiply 0.175 by 100. When pointer reading is equal to 14.5 centimeter, which is the same thing as 0.145 meter, the extension produced E is 0.145 minus 0.1, and that will give us 0.045 meter. Force F is unknown. Going with our formula for Hooke's law, we have F to be equals to K times E. Substituting in our values, we will have 13.33 times 0.045, and that will give us 0.6 Newton. So, students, with this, we have come to the end of our topic for today, part 1 of elastic properties of solids. I will now call on my colleague, Mr. Napoleon Kure, to come and summarize and then give you assignments to keep you busy at home. Stay safe and keep learning. Once again, I am Hassan Buki. Thank you. See you in our next lesson.
Hello, learners. You are welcome once again to another session of our e-learning program, the subject physics. As my colleague has rightly went through with you, the topic elastic properties of solids, part 1, is what we are looking at. And from what he has said so far on the introduction aspect of it, we're talking about some terms that have been defined, which are very important, qualitative explanation of what really happened when you have force applied to given solid. Now, with what he has said so far, you shouldn't forget the condition that must be written or must be applied when Hooke's law is obeyed, that provided elastic limit is not exceeded. That statement can come before or after that law, which is very important so that I don't forget. And with what he has said, F equals to KE is what we have as a basic formula on this Hooke's law. Force, which is the same as load. When the word force is mentioned, it's the same as load. And the extension is our E, our K, our spring constant. We use that to find either F or look for E or look for K, whichever one. And with that, we want to give you a work to keep you busy at home in form of assignment. 2 questions on our work to be done. Though it's not limited to these 2 questions, you have other things you can look at, looking at our references. Assignment 1, a string of natural length, 1.6 meter, is extended 0.004 meter by a force of 0.8 Newton. What will be its length when the applied force is 3.4 Newton? Question 2. Use the following data to determine length L of a wire when a force of 30 Newton is applied. Assuming Hooke's law is obeyed. On the table, you have the first box here contain force applied, or we can say load, and the SI unit is Newton. The second box under it is length of wire in millimeter, which is not the SI unit of length, but we take that one for that. And the first row, which is the force applied, the first value there is 0. Corresponding value for length of wire is 500.0, of course in millimeter. The second value for the second value of force is 5 Newton, and the second corresponding value of length of wire in millimeter is 500.5. Next is 10 Newton, having a corresponding value of 501.0 millimeter. And you have finally 30 Newton with an unknown value represented by capital L. That is what we have for you. Right. And our contacts are here. Hassan Buki, 080 65 50 4346. I take it again. Hassan Buki, 080 65 50 4346. Napoleon Kure, 080 36 36 2105. I take it again. Napoleon Kure, 080 36 36 2105. And we want to advise you keep learning and make sure you remain at home when it's not necessary to go out, and wishing you safety and the best in your endeavor. We'll be praying for you, and the Lord will bless you as you adhere to the COVID rules and regulation. Thank you very much.